Greetings from the Department of ECE, SJBIT. I am Anika, working as an Associate Professor in the Department of ECE, SJBIT. In this semester, you will be learning about microwaves and antennas with the subject code 1863. You can see here two parts we have. First part is consisting of microwaves, learning about the microwaves, and second part learning about the antennas. So coming to the first part, in the first module we will be discussing about the reflex klystron oscillator and its working, followed by the mode curves. Then the second part, microwave transmission lines along with the line equations and solutions, parameters related to that, and matching networks like stub matching, single stub, double stub matching networks. Then in module 2, microwave theory continues. Microwave network theory. In network theory, you will be analyzing the network using S parameters of a two-port and multi-port networks. Then in the second part, microwave passive devices we'll be learning about. In that, components, some of the components like phase shifter, attenuator, waveguide T's, E-plane T, H-plane T, magic T, coaxial cable connectors will be learned. In module 3, first part you can observe, which is about strip lines, all different types of strip lines, followed by the second part starts with antennas. So in antennas, the radiation mechanism, then understanding about the different parameters related to the antennas such as directivity, gain, antenna apertures, then efficiency, radiation intensity, bandwidth, polarization and different field zones. These things you will learn. And in module 4, first part is about point sources and arrays, second part is about electric dipoles. In electric dipoles, short dipole and lambda by 2 half wave dipole antenna you will be analyzing for far field and near field. Far field analysis will be done along with the calculation of radiation resistance. Coming to the first part, that is a point sources and arrays. Isotropic point sources, then followed by array of two isotropic point sources, extending the theory for n isotropic point sources. Then in module 5, we have a loop and horn antenna analysis, detailed analysis of that, then followed by different antenna types like helical antenna, horn antenna, aguda antenna, parabolic dish antenna and log periodic antenna. All these antennas used for with different applications, followed by analysis of that will be. To understand this, you need to refer the following textbooks. First two textbooks are for microwave, and second part is that is antennas part. You can refer JD Cross. For microwaves, you can refer to Annapurna Das or Leo. Then we'll start with module 1. So microwaves are nothing but the frequencies extending in the gigahertz range. Gigahertz meaning it is 1 into 10 power 9. So microwaves usually they'll specify it starts from 3 to 300 gigahertz range. So you can observe the electromagnetic spectrum, and as we know the relation between the frequency and the wavelength, and you can observe as the frequency increases the wavelength of that will be reduced. And in this slide you can also observe the different applications at different frequencies. So starting from extremely low frequency, very low frequency, and low frequency, medium frequency, high frequency, and so on. SHF, EHF range, and petahertz range, extremely high frequencies. And you can also observe the classification, which is from ELF range and followed by different frequencies and their applications you can observe. And the radio frequency spectrum, in the radio frequency spectrum or in radio frequency bands, starting with low frequency to tremendously high frequency, with a frequency range from 30 kilohertz to 300 and so on, with a difference of 10 times variation, and their particular applications will be seen here. So which is used in means the FM radio, and AM radio, cell phones, WLAN, wireless LAN, GPRS, GSM systems, and satellite 5G mobile system. Different applications will be seen here. And in the same manner, the radio frequency bands, they have classified according to your IEEE standards. They have classified the frequencies as the band designation shows. So HF, VHF and UHF range, that is a high frequency, very high frequency, ultra high frequency. Then from 1 gigahertz to millimeter waves, they have classified from classified into different bands based on that name, long wave, short wave, between S and X, then different names which they had given. So L band, which starts from 1 to 2 gigahertz, all these are in gigahertz range, that is your microwave band. Applications in this comes to microwave region. So S band comes to 2 to 4, and C band comes to around 4 to 8 gigahertz, and X band from 8 to 12 gigahertz, KU, K, KA, V, W and millimeter waves. And you can observe these are the IEEE standard classification of the radio frequency band in the microwave region. So your reflex klystron, the microwave component which you will use in the lab, will be operating in the X band region, that is 8 to 12 gigahertz range. So, and some of the application as we have specified with their frequency range, and you can observe here FM radio frequency, as you know already, which is in use, 88 to 108 megahertz. So 93.5 FM, and that's what here it is in between 88 to 108 megahertz range. And CDMA technology, which is in 800 range, and GSM 900 you have, GSM 800 you have, 1800 you have, and their frequency range uplink and downlink we can observe. And GPS, global system for positioning, which is in 1575 megahertz range. And 3G 4G, 4G range is in 2.4 gigahertz range, 2.3 to 4, and 3G, which is from 1.9 to 1.9 gigahertz and 2.1 gigahertz range. And even the Wi-Fi, which is from 2.4 range and 5.2.8 bands. So likewise, different applications and their frequency bands, as you can see. So as a basic understanding, to understand about it may be electromagnetics, to understand about your microwave or antennas, the basics which must start with history. So the history starts with James Clerk Maxwell. He is the one who proposed the four Maxwell's equations, which are well known to you in electromagnetic theory, which you have learnt. That is del dot d bar is equal to rho v, and del dot b bar. So indicating electric field intensity, magnetic field intensity, electric flux density, magnetic flux density, how they are related. Del cross E bar is equal to minus dou B bar by dou T. Del cross H bar is equal to J bar plus dou D bar by dou T. On this you can observe E bar indicating del cross E bar, curl product. So del cross E bar, if you observe, which is related to minus dou B bar by dou T, indicating electric and magnetic field intensities were combined. You can't segregate them. And the theory which has been validated by Heinrich Hertz. After him only we'll be naming all the frequencies in Hertz. Okay, then your microwave engineering theory history, if you observe, starts with Jagadish Chandra Bose, who had published, who had first public demonstration of the electromagnetic waves. Then later Alexander, he had published a paper on, that is in the journal on the same similar experiments, that is the demonstration of the electromagnetic waves. In 1901, Marconi, the first radio communication which has been demonstrated by him over a distance of 2000 miles. And in the same manner, Lord Ray had proposed the waveguides, hollow conducting structures. That is nothing but a starting of the waveguides, hollow metallic waveguides, 1930s, by two groups, Bell and MIT laboratories. And in 1950s, Robert M. Bartlett invented the strip lines. Now then 52 about strip lines. In MIT radiation laboratory, they have started with the X-band radar in 1942. After invention of your silicon transistor by William Shockley and Walter Belton in Bell Laboratory, they have started with a MESFET, gallium arsenide MESFET and gallium arsenide MESFET invention, which has been done in 1965. In 1970s, the Texas Instruments has invented solid state radar in the X band region. So if you look at the general theory, any microwave communication system which has to have the following blocks. So in the transmitter end, as you can observe, the baseband signal, whatever you have, which must be combined with a carrier, modulate the signal, modulate your baseband signal with a carrier signal using different types of modulations, as you have learned. That modulation, as you know, modulation is the one which you need to the purpose of modulation is to have a long distance communication. Then that modulated signal which may be at lower level, power level, so you can amplify that by using a amplifier. Then that amplified signal which has to be propagated through the free space, which can be done through antenna. But before that, impedance matching network is an important one to be made use between your amplifier and an antenna. The purpose of this impedance matching network is the impedance of your antenna has to be matched with the amplifier part, else most of the signal, instead of radiating into the free space or instead of traveling through the antenna, most of the signal will be lost at the input side itself. Then once if the waves will get radiated into the free space, that waves will be received in the receiver section through an antenna, receiving antenna. That received signal, which will be in milliwatts or sometimes microwatt, not even in milliwatts, microwatts, nanowatts region, nanovolts region, that RF power, as it is very low, so that RF signal which has to be amplified, along with noise it will get amplified. So RF amplifier we have, then followed by a mixer. It is a super heterodyne type. In super heterodyne type, we will be down converting that radio frequency signal to a intermediate frequency IF through your mixer and local oscillator. Then that IF signal, again it should be amplified through filtered noise, all those will be eliminated and amplified. Then the reverse process what you have done in the transmitter part, with transmitter section, which has to be done is a demodulation. After demodulating, that demodulated signal which can be made use for your purpose. So in general, in any communication system, it is a microwave or analog or digital, any communication system which has to have the following blocks. So in your syllabus, you will be learning about the microwave communication, microwave components, their analysis, and followed by how to radiate or how to transmit that in the second part. So if we look at the previous block diagram shows, you need to have an oscillator to generate the signal. To generate a microwave signal in the microwave band, that is from 3 gigahertz to 300 gigahertz range, the conventional tubes what we have can't be made use. So those conventional tubes, if I want to make use above 100 megahertz, so these are the following effects that will degrade the performance of your conventional tubes. So first one is interelectrode capacitance effect, IEC we call. Then lead inductance effect, together we call interelectrode capacitance and lead inductance effect, together we call it as a stray capacitance effect. Then followed by transit time effect, we will see soon. Then gain bandwidth limitations. Then the effect of radio frequency losses, like it may be a conductor loss, skin depth, that is I square R loss. Then for our dielectric loss. So the effects may be due to radiation loss also. All these will limit the conventional tubes to make use in the microwave region. So first and foremost, if you observe interelectrode capacitance effect, so if you look at the vacuum tube, the diagram shows. So the vacuum tube, if you observe, will have an anode, cathode and the grid in between. So electrons will get emitted from your anode and travel towards the cathode, and which will pass through the grid. And if I want to make use this device to generate the oscillations, and you can observe the dotted one between the grids, you can observe anode to cathode and gate to cathode, positive to cathode, that is anode to cathode. You can observe the capacitances. So these capacitances we call it as a inter-electrode capacitances. These three we call it as electrode, anode, cathode and gate we call it as an electrode in vacuum tubes. So between the grids you have a capacitance existence at high frequencies. So at low frequencies these will not come into picture. The reason for that is, as we know, Xc is nothing but the capacitive impedance, which is equal to 1 by 2 pi Fc. So now you increase the frequency, what happens? Xc value will reduce, inversely proportional. So as you increase the frequency, that is at very high frequencies, the impedance value of the impedance value is between the grid existence is very low, making the grids too short. So that is called as a inter-electrode capacitance effect. And which suppose if the grids get shorted, then instead of amplifying the signal at the output, you will get degradation, reduction in output. There we call it as a efficiency will be reduced, uh, which will limit the efficiency, overall circuit efficiency. And in the same manner, suppose you can observe the same capacitance effect, inter-electrode capacitance between all these three grids. So that is anode to cathode and cathode to grid and grid to anode. So CPK, CGK and CPG that you can observe with the dotted line and the capacitor. This represents the inter-electrode capacitance. Similarly, the lead inductance. Suppose once if the signal is given through that wire which will enter into your vacuum tube. That wire, once if you operate that at very high frequency, so XL value, which is 2 pi FL, if you keep on increase the frequency, what happens? XL value will also get increased. Once if XL value increases, meaning impedance is increased. Impedance increased meaning opposition is more opposition that you have. Instead of entering the signal into the structure, most of the signal will be limited at the input side itself. So you can observe the lead inductances at the leads at your cathode, anode and grid. You have a leads to connect to the external circuit. If you operate at very high frequency, the lead capacitive inductive impedance of that will be very high, which will oppose the actual signal entering into the device. So which will limit that output. So you can say that obviously even that lead inductances will reduce the efficiency or will degrade the efficiency. Overall circuit efficiency will be degraded. So that's what here you can observe. Usually you have three parameters of ordinary vacuum tubes become increasingly important at very high frequencies if you operate. Those are inter-electrode capacitance, lead inductance and electron transit time. So we had seen inter-electrode capacitance effect, which is between the grids existence. The capacitive impedance of that value will keep on reduce if you operate at very high frequency. Obviously that will make the grids too short, which will degrade the overall performance. Similarly, the lead inductance, so within the tube you can find out effectively which is in parallel with inter-electrode. Net result is directly on frequency limit. So the inductances at the of the cathode lead is common to both the grid and plate circuits. So this provides a path for degradation feedback. Degenerative feedback. Degenerative feedback indicating it is a negative feedback. You will be providing with lead inductances, you will be providing a negative feedback. With negative feedback, what happens? Obviously, the efficiency of the circuit will reduce. Similarly, if you observe the transit time effect, the transit time is the time required for the electrons to travel from cathode to plate. So this transit time is very less, or you can say that it is very insignificant. at low frequencies. If you operate the device at low frequencies, this is very insignificant, not to be accounted for. Suppose if the same circuit, if you operate at very high frequencies, the transit time becomes an appreciable portion of a single signal cycle, because if you operate at high frequencies, f value increases, meaning what about the lambda, which is inversely proportional to frequency, obviously reduces. The length, the wavelength is in proportion to the transit time, that is the time taken for the electron to move. As they are in proportion, or as they are in comparable range, which will affect or which will degrade the tube efficiency. And that's what transit time in excess of zero point 0.1 cycle causes the significant phase shift. So with that phase shift, which will account between the plate current and the grid voltage, results in significant decrease in tube efficiency. All these three in the same manner, the previous effects what we had seen, limits the conventional tubes to make use at very high frequencies is gain bandwidth product. Gain and bandwidth, usually they are inversely proportional. So if I want to try to increase the gain, obviously which will have an effect on bandwidth. Similarly, bandwidth, if I want to improve, will have an effect on gain. So the bandwidth gain product, which will limit the tube to make use at very high frequency. In the same manner, other effects like radiation loss and skin depth effect, that is a suppose as I am using a material for vacuum tube, in the vacuum tube or in the device, microwave device, whatever you make use the component, that component dielectric losses are dielectric losses are the conductor losses, which will make the efficiency of the component to reduce. Similarly, the radiation losses. Radiation losses means I want the once if I give an input signal, then instead of amplifying the signal, suppose the signal is getting radiated into the free space, so that loss which I wanted to decrease, if I operate at very high frequencies, instead of amplifying the signal, some of the signal will get radiated. So that radiation which has to be eliminated. So all these effects which will reduce or which will the conventional, which will limit the conventional tubes to make use at gigahertz range, that is in the microwave range.